Hello. This video is on the concepts of isomorphisms. And that is a special case of more general, more weak-one homomorphism. Of groups. And this general notion is just a way of comparing groups, and this is a strong comparison, really identifying them. So how do we compare sets? Well, we just map them. We have functions between them to compare them, and that is the same way for groups. So we have a function or a map between two groups, and this map is called a homomorphism, a group homomorphism. If it aligns operations, what makes groups groups, what makes GG a group and H a group, it's their operations. And this map is to align them in the following way. So we compute the operation in G, that is X and Y taken in G, and then we map the result to H. Alternatively, we could map X and Y separately to H and then compute the operation there. The results have to coincide. That would make a map a homomorphism. So that is happening for all possible pairs of elements. So here's an easy to check fact, but still better to be checked, that if you have this property for a map between groups, then the identity element will have to be mapped to the identity. You don't need to postulate it, it will happen automatically. Similarly, for any element, I'll call it G now, the inverse to this element will be mapped to the inverse of its image. So again, it's a consequence of this definition, you don't need to assume it. And that is believable because, again, identity and inverses are sort of sugar on top of that operation, are conditions. Them being around is a condition, not a structure with respect to the operation. So if you preserve the operation, the conditions will be preserved. The identity must go to the identity. But it's interesting to prove it. So that is your exercise. So now I will define what is to be an isomorphism. So a map between groups is an isomorphism if it is a bijective homomorphism. Well, that's really a mouthful, but what it really is saying that we have a bijective map identifying H and G as sets, and moreover we identify interesting structures on them, the operations. So that is what an isomorphism is. Informally, it's just relabeling your group elements in G in the labels of H, such that the operation tables, if you record your operation as tables, identify, and that is it. And let's just close by looking at examples. I'll start with homomorphisms. Plenty. Say integers to themselves. Take an integer, multiply by any number, say 2, by any integer number, of course. It will be linear, which is to be a homomorphism in this case because our operation is addition. Take integers and reduce them modulo fixed modulus n. So just replacing an integer by its congruence class is a homomorphism, is a surjective homomorphism. This one was not surjective, not every number is even, but it was injective that way. So plenty of homomorphisms. we'll have them more, say, sign. We had it before looking at permutations. Taking a permutation of an element and computing its sign gives us plus or minus. The sign rule, which says that the composition, the sign of composition is product of signs, is the homomorphism rule. So we have another example of a homomorphism. And I will continue here with examples. So maybe the exponential function from real numbers with addition to real numbers with multiplication but without zero. So x, real number, is mapped into the exponential of x. Addition, which is the operation here, is transformed into multiplication, which is the operation here. So it is a well-defined map, it is a homomorphism. Let me complexify it, upgrade to complex numbers. So I still have a way of taking a complex number which is in real coordinates x plus I, y, and transforming it into the exponential of that complex number, which is a product, say, you can write it as a product of two exponentials, exponential of real x and the exponential of imaginary iy, and the second one, according to earlier, we can just write as cos of y plus I sine of y. And again, the complex multiplication rule guarantees that this map transforms addition into multiplication. It is a homomorphism. So that homomorphism was not really surjective because negative numbers were not in its image. This homomorphism is surjective. That homomorphism was an injective homomorphism, sending things, different elements, different real numbers, different answers. This is not. Please check that bit out. So let me sort of continue with more examples, but now of isomorphisms. A kind of iconic isomorphism is between integers mod n under addition, with addition, and roots of degree n, complex roots of 1 of degree n. And the map I'm thinking about is the following. So just take an integer first and then transform it into, well, this number, but with I, the prefactor of I, and really the prefactor of 2 pi I. 2 pi I over n, that many times. So then you could see that this way you really see all the, you really encounter all the roots of degree n. You encounter them once. That is a bijective map, and moreover the addition here is in alignment with the multiplication here. So we have an isomorphism of groups. These groups are the same. More interesting, let me finish with more interesting identification. Let's take integers mod 4 with addition, and here we will take integers mod 5 but with multiplication. Still I claim that they can be identified. And it's supposed to be an exponential sort of map, transforming addition into multiplication. And here's my formula. So I take integer mod 4, or any integer for a start, and then I'm turning it into the power of 2 to that integer. I'm computing with mod 5, the answer. So why am I so sure that it is going to be a surjective map? Because the order modulo 5 of 2 is, well, it can be only 2 or 4 or 1, of course, but 1 is not an option for non-trivial 2. So if it's order 2, 2 squared, which is 4, has to be congruent to 1. It's not. And it is, of course, order 4, which means that all 4 powers of 2 are different, and hence they will be corresponding under this map to different elements in the integers modulo 4. So we have this map defined from the start, because the cycling is guaranteed to be of cycle 4 by the Fermat theorem, but the map is surjective if the order is exactly 4, not smaller, not any divisor. And it is. And let's finish by tabulating this map. So listing the integers mod 4 on the left, before the map, integers mod 5, but under multiplication after the map, and then just making them aligned. So there will be 4 of them. 0 goes to the 0th power of 2, which is 1. 1 goes to the first power of 2, which is 2. 2 goes to the square of 2, which is 4. 3 goes to the cube of 2, which is 8. But that is congruent to 3 mod 5. And so we see all the invertible integers mod 5, 1, 2, 4, and 3 are listed as values of the homomorphism. So the homomorphism is manifestly a bijection. It's actually, you could start guessing, it's actually more generic. I can replace 5 by any prime and I will still be seeing an isomorphism between integers under addition modular that prime minus 1 and integers modular that prime with multiplication. But that is a bit deeper fact, so we'll discuss it sometime later. See you.